Okay, so we have y here. Okay, so let me choose my pen. Okay, on the y-axis we have the basically, okay, on the x-axis we have the feature x, and then on the y we have the prediction values and the actual points. Okay, the actual points are these circles, okay, the gray or black circles. The actual function that created these points is this black line. Okay, and it created those points, and then there is some irreducible error to edit to those. But then basically we take those points, fit different models to these points. We have 3 different models: the yellow one, the green one, and the blue one. So you see the yellow one is the simplest one, the green one is the most complicated one. And so if you look at this figure in the middle, we have mean squared error on the y-axis, flexibility on the x-axis. So yellow was the simplest one, that's here. And the green one is the most complicated one, and that's here. So then what's the gray line? That's the training error. So training error will always decrease, you see. Keep decreasing if, until it reaches 0, I would say. But the red one is the actual that we are more concerned about. That's the generalization error or the testing error. So it decreases until this blue point, and then it starts increasing. So this place is where it underfits, and this is where it overfits. So here the ideal model would be this blue one, because it's the lowest testing error, and then it starts increasing afterwards. And you can see that from this figure as well, because you see that yellow is too simple, it's not doing a good job. Green is too complex, it's not doing a good job, but this blue one is doing quite a good job here. So then the next step is looking at this figure here. So what does it do? It shows the how the variance and the bias changes. So red is a testing error. Okay, so you see it's this one, the same plot, it's same line as this red one here. So you have that, and then we said error is basically the addition, the summation of bias and variance. So that's what these 2 lines are. The blue one is the bias, so bias is decreasing as you have a more right, it keeps decreasing as you have more and more complex model. Bias will decrease because your predictions will be much closer to the actual data points, right? You can see that from this green line behavior here. And this yellow one is the variance. So variance is increasing because you see here it's overfitting on the right. That's why the variance is quite high. Here it's underfitting on the left side, so that's why the variance is quite low. But if you have more and more complex model, it will go to overfitting. Okay, so here we are tying all this bias, variance, overfitting, underfitting, and error terms together. So a second example, by the way, these examples are taken from the Introduction to Statistical Learning. So here are the data points. So the function itself, this black line, you see it's actually quite simple. It's not like before. So here a simple model will do better than a more complex model. And you see that actually from this line, from this graph here in the middle. So you see the simple yellow line, and then blue is also still simple, are doing pretty good job. But then when we go a bit too complex, we are really overfitting quite a lot, and so our testing error is quite high. But again, the training error will always keep decreasing. It's always like that. Training will keep decreasing. So when I look at the bias and variance relation, so gold is the variance line here. So again, since I'm reaching overfitting towards right, the variance is increasing. Bias is not changing too much. Because why? Because even at the simplest scenario here, bias, meaning the difference between our predictions and the actual points are still quite low, because the actual function that created these points is a simple function. That's why predicting with a simple function will still do a good job. That's why the bias does not change too much, right? This is the another example. So the model, the black line is like so. Okay, so you see the gold line is not doing a good job. It's pretty bad because the actual function that created these points is actually a pretty complex model. So if simple line, the gold line, will not do a good job. So it's quite high, the mean squared error. Blue is pretty good. Even green is still not bad because, again, the idea is the function, the black function line, the actual function underneath these points that create all these points is itself very complex. So here, although the complexity increases quite a bit, you know, we don't see that harsh behavior of overfitting, and you can see that here as well. So bias is very high at the beginning, but then at blue, you know, at this mid area, even in the area of overfitting, it's still quite not bad. It's not too bad as before. Okay, so basically by looking at these kind of graphs, we can assess whether our model is suitable or not. Okay, how complex our model should be. Okay. So another example shown here with some actual calculations of R-squared values based on whether it's underfitting or overfitting. So in the high bias model, it underfits the data, right? Our model is underfitting. So the training score is 0.70. And for example, based on the red points, which were the validation data points, R-squared is 0.74. So both of them are close to each other, and they are quite, you know, they are not very good. Okay, and that's the idea of underfitting. Both of them will be bad. When we go to overfitting, so now overfitting means overfitting to the training data, right? And you see a very high score in training data. But when you look at the red points, which is the validation point or testing score, which means, you know, it was trained on the blue points and then it was tested on the red points. So it did not see the red points before. So now you see how bad this is. This is extremely bad. It's minus 1.8 to the times 10 to the power 9. That's extremely huge in the negative direction. That means it's super bad. And you can see that behavior. Why? Because this line is overfitting so much that it goes really the extreme to fit through all these blue points, right? So it's seriously overfitting. Now when new points come in, it's doing a super bad job on them. It can't really predict them very well. Because look, just for this one, the actual point is this one, right? But my curve is all the way up here. I don't know how far it goes, but the prediction is here, let's say, based on this point. So you see this huge gap between this. So even this simple line is doing much better than that because the point is here. My prediction will be here. So the error, you see, the error is much lower. So this is, again, this is why we should not rely on training data accuracy calculation or error calculation. It will be, you see, if we were to do that, we would think our model is doing very good, 0.98. But in actual, on new data set, it's really tanking very bad, right? So that's why we can't rely on training accuracy or training error metric. Okay. So how can we diagnose whether there is overfitting or underfitting? So these graphs that are here, we can draw them as well. So these graphs are called the validation graphs or curves. We can do that. We can also create learning curves. Okay, so basically learning curves and validation curves are our friends that help us to diagnose whether there is high variance or high bias problem or overfitting or underfitting problem. So learning curve, it basically plot model training and validation accuracies as functions of the training data set size. So as we increase the training data set, how does the model behave? Validation curve is just what we saw. We plot the model training and validation accuracies as functions of the values of the model parameters. And the goal is to detect whether the model suffers from high variance or high bias. So learning curve looks like this. So basically this the training set size. So let's say there's only 1 point here that we use for training, and maybe 10 points and so on. Let's say, you know, I don't know, in some increments. So we just want to see whether by increasing the training set size, what happens to the validation curve, validation score, and the training score of the model. So you see, in general, the training score will be will start to go lower, because when you have only few points, it will basically just overfit to those training points. And when you have more and more points, it will basically start to act more normal and it will decrease a bit. The validation score will increase because at the very beginning, you know, since the model didn't learn, or basically just overfitted the training data, it's not doing any good job at all whatsoever. So it's just overfitting the training data, but it's doing a very bad job on the validation data. But then if you increase the dataset points, so the model is learning basically more and more from the data, and now it's doing a better prediction on validation set. Okay, so that's what learning curve is. Validation curve, we have already seen this. So we have model complexity on the x-axis and the model score on the y-axis. So as we increase the model complexity, the training score will increase. The validation score will increase up to a point, and then it will start decreasing after that. Okay, so by both of these curves, we can detect whether our model is high variance or high bias, you know, suffering from high variance or suffering from high bias. So here, for example, there's another example on learning curves. So if we draw the learning curve and we see a graph like this, and let's assume that we have a desired accuracy, let's say based on domain knowledge or some past experience, maybe from other people, we know that, you know, overall we can achieve, let's say 90% accuracy or 85% accuracy, but we are getting, let's say 60% only. So then we know that our model is actually underfitting and there's high bias. If you get a graph like this, you know, basically the idea here is that the training accuracy is quite high, but then there's quite a large gap from the validation accuracy curve. And so this large gap basically indicates, okay, there's overfitting. So overall, we want our model to have, you know, close to our desired accuracy, but then also, so meaning overall a high accuracy, and the training and the validation curves should be close to each other at the end. So they should like converge to each other at the end. Okay, that's the idea of learning curves. So how can we address, okay, so we learned about all this different occasions and different scenarios regarding high bias and high variance. What can we do to address high bias and high variance? The high bias model will have low accuracy, so that's right, that's underfitting. High bias model has both low training and cross-validation accuracy, so both the training and the cross-validation accuracies will be low. So what can we do to solve this problem? Increase the complexity of the model, that's one way. Increase the number of parameters of the model, so by collecting new features or constructing additional features, that's another way. Or we can decrease the degree of regularization in models where regularization is used. And these can include support vector machines or logistic regression or neural networks as well. So these are the possible remedies for that. What about addressing high variance? So high variance can be identified by the large gap between the training and cross-validation accuracy. So the possible remedies include collecting more training data. So the data should not be too noisy. The model should not have reached its capacity yet. Okay, so it should not be optimal yet. Because if it's already optimal, there's not much you can do even with more data. And if the data is too noisy, that also would not help. Another thing we can do is reducing the complexity of the model, right? Because we are overfitting, so we want to reduce the complexity. We want to have a more simpler model. We can increase the regularization of the parameter. Regularization parameter, that means we can apply more penalty on the parameters of the model. So then it will be basically regularized and it will become simpler. And for unregularized models, we can decrease the number of features. Okay, so feature selection, dimensionality reduction techniques can be useful. Okay, so that's it. I have some references here that I used in these slides, so you can check them out. Some recommended readings that you can look into as well. So thank you and have a good day.